Before I delve into front-end development, or rather the HTML5 and JavaScript side thereof, I've been doing programming on the other side, like for desktop environment called KDE, and then cross-platform C++ library called Qt, and lately also WebKit. Now, throughout this progression, I realized that if you're a front-end developer and you try to create web apps in certain ways, it would be very nice if you have knowledge about how browser works, or in this particular use case, how WebKit works, because that gives you a different understanding and different perspective on how you create things. So today, I'm going to cherry pick some of the topics that I'll hope it will be very useful for you the next time you try to create web apps. So a little bit about WebKit itself. WebKit was created as initially as a fork of HTML from Apple, and that was almost 12 years ago. If we look at the revision, and as you can see right now, it's just almost everywhere. If you use a web browser, likely it will be based on WebKit, mobile devices, and application runtime, etc. Now, if you see this progression, you can see how operating systems and browsers adopt WebKit along the way. And on the vertical axis is the revision, meaning check-ins, and you can see we're approaching 150,000 there. And that's a lot of code. And if you calculate this is approximately 3,000 commits per month. And I don't know about you, but that number is like scary. I think Linux kernel beat this because it's like 5,000 commits per month. But if you are about to build a development team and try to work in such a development pace, that'll be pretty difficult to handle. That's why WebKit is very heavy on test-driven development, even before it was becoming a buzzword. And if you check out WebKit repository right now, guess which one is the test portion? That one. So just about 10% of your checkout will be code. The rest, they're just tests. There's a running joke where people say WebKit is a bunch of tests, and the code is there to make the test pass. And WebKit has a very nice concept of social layers. I think this starts to be adopted in many projects as well. So every contributor starts by sending patches to WebKit, and after a while, you will be, or someone can nominate you as a committer, where you have direct access to the repository. So this doesn't mean that you can just commit stuff like crazy. Every patch needs to be a review. And after a while, probably about a year after you contribute so many patches, then someone can nominate you as a reviewer. This gives you an extra rights of reviewing patches, meaning you can accept, reject, give reviews, etc. So for example, YUI project, I think they start to adopt this kind of social layers. Now, along the line of heavy on TDD and then a big team, 1,000 commits per month, this allows someone to get familiar with WebKit code first and then work to become committers. And after a while, when he's comfortable working with a huge code base, then he can start reviewing others' patches as well. There's very nice statistic and analytics on who are these committers and reviewers. They're still mostly dominated by big companies like Apple and Google. And as you see the commit rate, the right side chart there, it shows that Apple has been doing this for a while, obviously, and then Google catch up with the development. Throughout this presentation, I'll sprinkle links here and there on the slide deck so that you can follow it up at home if you want to find more further information about this. So if you look at the browser at the high level, this applies not only to WebKit-based browser, but any other browser as well. What you see is usually just the user interface, and underneath that, there's the browser engine. And it embeds the rendering engine, which is responsible to display your contents as pixels on the monitors. And because you need to save everything from storage to persistencies, cookies, and everything, then there's a way to store that for you. And the rendering engine needs to interact with the network because it needs to pull the data off the server, JavaScript engine because sometimes you want interactivity, as well as graphics stack. We're going to see what graphics stack is in a couple of minutes. So WebKit component itself, usually people talk about web core and JavaScript engine. There are two JavaScript engines that can be used with WebKit, JavaScript Core or JSC. The marketing term for that is Nitro. It's the one that is built in, and it's used by Apple on Safari and mobile Safari. Google, however, use different JavaScript engine. I'm sure a lot of people know about this, V8. But they also share the same web core, and web core consists of a lot of modules from HTML to Canvas to SVG and so on. The design of WebKit itself is following the pattern called platform abstractions. So if you see this diagram, Chrome and Safari, they share the same parser, they share the same CSS selector, they share the same SVG modules and Canvas implementation. But the way to output that operation and then show it to the screen or even interact with the timer, they're all different. So that depends on the browsers, operating systems, and many other factors. This makes sense because if you try to get some data over HTTP on Windows, the API to do that is completely different than if you want to do it on Linux. And that applies to anything from Clipboard. Clipboard is probably the most glaring example where every operating system does it differently. And geolocation as well, because on mobile devices, the way to get your location is different than, say, on the desktop or laptop, if at all. So one of the most frequent asked questions about WebKit is why two browsers using the same WebKit, they behave differently? And this is the explanation, because underneath that, they might use different graphic stack. They might use different ways to implement certain abstractions. It's as if you take two same engines and put it two different cars. Sometimes you get different performance. Or put it in two different airplanes. You don't want Airbus pilot to land a Boeing airplane, for example, just because they use the same engine. There are many other factors that makes airplanes different. So let's take a look at the first important blocks of WebCore, which is the loader and parser. Loader is responsible to get something and load it, possibly from remote server. And then parser is responsible to consume that data and then make something useful out of it. And if you look how they're related, both HTML and CSS, they have their individual parsers, and then HTML parser will construct something called the DOM tree, and then combined with the styles, this will build a render tree. So loader itself is ridiculously complicated. There's a nice blog post that explains how this works. Basically, there's two pipelines. One is loading for the document loader itself, which is responsible for loading the document contents. And then the second one is for resources, such as scripts or images or style sheets that's part of that document. What is important here is that if you build a WebKit-based browser, then you can tweak the way, for example, if someone clicks on a link, do you want to have the navigation policy that follows that link and then open it a new page, or do you want to completely block that? So in some cases, this is necessary for example, hybrid HTML5 runtime environment. And then there are cases where if browser finds that this document cannot be understood, say it's not CSS, not HTML, then, for example, on PDF. So what do we do? Do we need to open it in a PDF viewer? Do we need to save it? Do we need to ask the user, etc.? So that's why it's slightly complicated there. It's different than inline resources or embedded resources because you're supposed to consume that as part of the document. And sometimes the data that you have might not come straight fresh from the server, but in some ways or others have been stored by the browsers. And these are just some of the list of possible cache in Chrome. There are 10 and more. So one of the nice things about having being able to parse HTML is something called Tokenizer. So the Tokenizer is responsible to split this into tokens. If you see a simple text here, then the Tokenizer will recognize there's a tag called HTML and body and P and so on, and those are tags. So this seems easy, but if you read the specification, how many of you here have read HTML5 specification? Yeah, if you try to print it, it's several hundred pages. And tokenization involves 70 states. So it's not easy. It looks from this example as pretty straightforward, but it is not. So after we recognize all the tokens, then the next step is to parse it. The job of the parser here is to build a DOM tree out of your HTML document, and usually this involves a process involve a module called tree builder, where it is fed by the tokens and then try to construct the tree. HTML5 parser, specification compliant, is also very difficult to build. In WebKit itself, it's about 10,000 lines. And again, if you read the specification, it's quite not trivial. The nice thing of all browser confirmed as the same new HTML5 parser is that they will produce the same DOM tree even if the document is broken or you have mismatched tags, etc. So they sort of define the same behavior. New in WebKit is threaded HTML parser, which means that when it parses your document HTML, then it does it in a different thread, so it won't block your UI. This is quite important on mobile device with limited resources. So from Tokenizer, we can extract some useful information, and this is something in WebKit called as the Preloader Scanner. For example, if I parse CSS and I find import, then I can immediately fetch that URL referred by that CSS. That's my style sheet without waiting until the CSS, the style sheet is fully parsed. Same with HTML. If I see there's a script tag, there's an image, then you can start to schedule a network request that pull this resource off the server. This is an example where if I just open sencha.com and there's a bunch of resources that are fetched even before the document is completed. Very useful to optimize network performance. So that's loader. We got data, it's been tokenized, it's parsed, and we got DOM tree. Now we enter something called layout. A lot of people use the term reflow. I prefer layout because that's what CSS specification says. So this is DOM tree. If you work with JavaScript to manipulate the document, you might be familiar with this. It has a standard, and basically from that text, it will construct the tree that match the way you will expect it. This is the actual WebKit class name, and nicely matched to that HTML5 specification. So the DOM tree itself doesn't say anything about how to paint those trees on the screen as pixels, and therefore WebKit has something called render tree. So the render tree implements the CSS box model. Again, a very long specification, and they usually match one-to-one. So if I have a HTML document, then there's a render tree called render root, and there's a body, and there's a text. The render tree is also used to navigate the tree structures and then do a matrix. So if you click on a button or mouse over, then it knows that render tree needs to correspond to which DOM tree. Obviously, if you read the CSS box model specification, you need to be able to find styles for your rendering. And it's tackled by something called render style. This is yet another tree structure. And roughly, in layman's term, this corresponds to computed style if you do a DOM analysis there. So if, in some cases, you don't have a render tree. For example, if you set the display property to none, then there's no render tree associated with that because there's no need to display that particular node. So there's so many trees in WebKit that's it's confusing. So we have DOM tree, we have render tree. How do we create those? This is something called attach process. Historically, it's been called that way since KHTML time. So the logic is a DOM node is invisible, and then you attach it to the main view to make it visible, and therefore it's called attach. So if I have a DOM or element, in this case a div, and then create a render object associated with that, that's called attachment, and then WebKit can display it as part of the main view. Again, for a particular node, you might have some style. Too many trees, so we always joke sometimes it's a forest, it's not the trees anymore. WebKit is a collection of a lot of trees. Attachment process is also as complicated as a loading process, and this diagram captures just partial of the actual attachment process that happens inside WebKit code, more precisely web core. So there's a huge difference between style recalculation and layout. Layout involves metrics and geometry. For example, if you move one div to another place, then obviously the position change. Styles means only to Style recalculation means style resolutions, solving a particular style properties for each node. So probably an example here is if you change the top property of the style, then WebKit needs to paint a larger area because the position might change. But if you just change the background color, then the rectangle that is affected by that change will be pretty limited because it doesn't move to another place. I'll show you some demo later on. So getting the right style involves CSS selector matching, because you might have a style in your style sheet that defines the color is blue, and then you need to resolve it if WebKit finds a paragraph element. And again, this is stored in render style. So there's a lot of tricks to minimize the layout, and this is usually involving avoiding touching some properties that causes geometry / dimension recalculation. There's a long list there. Sometimes there's also a best practice where you try to avoid one property after another and do batch processing. So we got the document, it's parsed, it's constructed as DOM tree, and then the layout process creates the render tree. Now, how do we paint that? So the goals of painting is obviously to visualize all the render objects as pixels on your monitors. Every painting commands goes to the something called graphics context abstraction. I referred to platform abstraction earlier. And then there's a particular optimization that can be made there, where, for example, if that particular render object is not visible to the viewport, then it doesn't need to be painted. And of course, to handle transparency, clipping, and so on, again, this needs to follow the back-to-front algorithm. Graphics abstraction means that every WebKit-based product will use different graphic stack. We can see that Mac and iOS, they fall into Core Graphics, and Chromium Android use Skia, the rasterizer from Google. And there are others, toolkits, Qt and GTK, that use their respective graphic stack. To put simply, inside WebKit core itself, you will not be able to see calls to particular Core Graphics API or even Skia API. So it will simply call graphics context. As an example, if graphics context has an API call, please draw a rounded button somewhere, then it will call the corresponding Core Graphics API to create or to paint that rounded button. So if you have a graphics stack that doesn't understand rounded corner, it means that your button will look either rectangular or completely weird. CSS Painting is, again, not easy. It involves 10 stages from defining the outline, background, etc. So the way WebKit does the painting, or web core, is to ask every render objects, please paint yourself according to these 10 stages, and then it follows from back to front with the proper tree traversal based on your z-index. If you build a WebKit-based browser, the painting request can be asynchronous. For example, the browser doesn't need to paint certain areas if it's outside the viewport. If your page is very long, it doesn't need to paint the bottom part of the page if you're still at the top. So that's one way the browser requests that to WebKit. The other way that happens as well, for example, if the page has a script that changes particular colors, then WebKit needs to tell the browser, hey, that rectangle has been invalidated. We need to paint it again. So two ways. Now, if we talk about graphic stack, the responsibility of graphic stack, again, to draw shapes, and in the concept of PostScript world, where all graphic stack usually follows, path is everything. This is different than Unix. In Unix, file is everything. In the world of graphics, path is everything. So path is a general form of curves. Everything else is a subset of path. In order to make path appears on the screen, it needs to be stroked and filled. This demonstrates the cheapest possible stroke and brush, which is on the left side, and the most expensive possible stroke and brush. So if you want your page to be performance, just use solid colors and no fancy dotted lines, etc. This seems trivial, but this allows you to do a feature cost analysis. So how much I will go from the designer perspective, tweak the page so it looks beautiful, but at the same time, what kind of performance that I will sacrifice. Painting is also complicated because people, paint or draw text. It's very hard to imagine web without text, and texts are just curves because those glyphs are crazy. And in many graphics tag, curves cannot be painted directly, so it needs to be broken down into a series of polygons. On top of that, we also have anti-aliasing support so that all the jagged edges, they all look smooth. This is why I'm pretty excited with high-density display, such as Retina technology, because at one point, we might not need to have anti-aliasing anymore. And of course, in some cases, you want things to animate, rotate it, or have a 3D perspective and so on. This just complicates the work of a graphics tag. So painting, that's general painting, and I'd like to touch a little bit about hardware acceleration, in particular in the concept of WebKit. Usually when front-end developer talks about hardware acceleration, this is all we refer to, right? It's just a matter of waving your magical wand and then cast the spell, translate 3D. This is unfortunately the very perverted view of hardware acceleration within the context of WebKit. And I'll tell you a bit about that in a couple of minutes. So many devices, phones or desktops even, they use system on a chip. So in your CPU, it has everything. And if you look at the particular GPU, or rather the block thereof, it has particular properties, mainly because this has been designed for accelerating games and not anything else. So it has fixed geometry, and it can do some transformation, and most of the time, it's optimized for rendering textured triangles. It's not a surprise for many graphics programmers that sometimes drawing a straight line is slower than drawing a triangles. If you're familiar with games development, this is typically the way people use GPU. So define some vertices, points in the space, and then you apply some transformation, and then it will be rendered, and then you can possibly texture it so it looks more realistic. So the efficient use of GPU by WebKit involve certain levels. First is obviously to accelerate the drawing primitive. I mentioned how anti-aliasing and curve and polygon, they're very difficult to handle. This could be delegated fully to the GPU. So if you use Mac or Safari on Mac, which uses core graphics, as well as Chrome and Android that use Skia, those graphics tag knows what kind of platform they're running on. And for example, it can detect, oh, my GPU is quite powerful. Now let me delegate some of the drawing primitive into the GPU. So without you realizing it, without those magic translate 3D and so on, sometimes the browser already use hardware accelerated graphics. What I want to show next is something called backing store and compositing. So when you build user interface that needs to be responsive, sometimes you want to decouple the user interaction between the rendering itself. And a typical example for this is maps. How many of you use Google Maps? Yeah, a lot of people use Google Maps, and you don't need to wait until Google Maps downloads all the tiles before you can pan around and zoom and do crazy stuff with it. So the process of downloading the tiles is separated from the process of maps responding to your user interface gesture. So in WebKit, many WebKit-based browsers implement something similar. So the rendering doesn't happen straight to the screen, but it goes through something called backing store. And this diagram illustrates it, that backing store is style. I'll explain a little bit why it's style. So when you zoom in, scroll, pan, and move your fingers on the screen, on the touch screen, what you do is manipulate the backing store. So totally decoupled. If you own the very first version of iPhone, sometimes you can notice the checkerboard pattern. How many of you have seen this? Yeah. These days, you don't notice that anymore because the phone is so fast that it catches up pretty quickly. But in the old days, yes, if the page is complicated, you scroll very quickly, then momentarily for a couple of 100 milliseconds, you don't see any contents there. And this is exactly because the backing store has not been updated to contain that portion of the contents yet. And if you pinch to zoom, that even happens today. Sometimes you see blurry rendition of for example, in this case, your SVG. So that's something called progressive rendering. As you zoom in, zoom out, the browser just displays the scale version of your content. And then when you stop, or whenever he has some time, then it tries to render your content with a high resolution. So basically, you can transform your finger movement, your gestures, into just matrix manipulation, because panning means just translate up and down, and then zoom means just scale it. So if you look at this time diagram, from the moment that you pinch on the screen until you stop, there'll be two processes happening there. First is to display something quickly, as soon as possible, although it might be blurry, blocky, and not perfect. And then after a while, you're going to see something sharp on the screen. So this is the trick that has been used by many games, CAD application, and many other typical graphics-intensive application for a while. And we've seen that in browsers. So if you use the latest iPhone or Android, then all the browsers there use this kind of technique. So backing store is usually tiled because what you can leverage the concept of texture streaming. Instead of drawing a huge backing store and send it at once, you can just split it into small tiles and then send it by one. This is why the checkerboard pattern happens as well, because it doesn't update the entire screen, but it just updates a portion of the screen. We can extend that concept further. So instead of just huge backing store for the entire page, what if we have a backing store for each element? And that's called something as layer. And WebKit does use backing store for elements that, for example, has 3D transform, or if it's a video tag, or if it's canvas or plugins, and if you do a CSS animation and filters. And for animation, this is wonderful because the way animation works, there are two steps. First is the initialization. So you just want to see, hey, I want to animate this element. Please put it in the GPU. And then the animation step happens. This happens for every frame, where you manipulate that element while it already resides in the GPU. So when you see a demo, how many of you have seen WebKit Leaves demo? Hold on. This is a pretty famous demo back then. So you see leaves falling from the top, and those images, they are individual layers. So for every single frame, WebKit does need to draw that image again and again on a different position, because it already stores everything on the GPU. You just need to tell GPU, hey, it's the same leaves, but now different position. So the rightmost diagram shows that that's how it's visualized inside the GPU. So you put layers one after another, and then we just manipulate the layers. The modules that are responsible for handling those layers often called compositor. And one of the responsibilities to do twinning, because if you want to move a box from one place to another, if you want to have a smooth animation, then obviously there are twinning steps involved there. New in every browser engine is using compositor in a separate thread. Again, this so that we can have the advantage of exploiting the multi-core processor and not blocking the UI thread. Core graphics via core animation does this very nicely. So if you want to debug all this layer in compositing, with Safari, there's a very easy way. So you just need to type this on the terminal, and then suddenly you have an extra debug menu on your Safari. So I'll show you here. There's drawing compositing flags, and you can disable show compositing borders here. And that's why you see the borders, yellow borders there, because if I open this in my other browsers, well, the demo doesn't display any borders, but because Safari draws some borders around those layers, then you can witness those composite layers. So the borders, the colors indicate something, but what is very exciting is that each of these borders, each of these rectangles displays a number in the corner. I don't know if you pay careful attention. There's a 66 over there, and there's 2 over here. This represents how many times WebKit has captured that element and then sent it to the GPU. That is very important because you need to optimize the amount of, you need to minimize the amount of texture upload. If you use mobile browser like Chrome for Android, you can even enable this straight from your browser. you just need to go to Chrome flags and then enable something. And then in addition to that, this head-up display also display the frame rate chart, how many frames per second your browser renders the page, as well as the amount of GPU. It's not really visible, but here I can see that it's using 25.5 megabyte of 256 megabyte of GPU memory. We'll see that optimizing the animation or even web page in general to minimize the amount of GPU memory is extremely critical. So in order to avoid texture upload, there are only a couple of things that you can do. So as long as you animate the opacity, or animate means also change the opacity, move the element here and there, and then change the size, and playing with the geometry, and do some filtering, that's fine. There's no need for WebKit to capture that element again and send it to the GPU, but everything else is dangerous. So this, for operation, this is usually what people often refer as hardware accelerated CSS. So constant texture upload is really bad. Let's give an example here. So I have a box that changed the color from green to blue, and I also move it so that it's visible. And now you can see that the number keeps increasing. It's because if I change the color, then WebKit needs to capture that element again. Just imagine this is capturing as an image, and then send it to the GPU. So changing the background color causes a lot of texture upload. And if I keep adding this, if you do it on your phones or low power device, at one point the animation will stop completely, or it will start to skip frames, meaning instead of going gradually from blue to green, it just shows blue and then a couple of seconds later green, and so on. And if you use Chrome for Android with head-up display, you can see that this totally saturates the GPU memory. So if you do that, I need to close this. If you do that, no amount of Translate 3D in the world will save you. Now, if you just play with transformation, whether it's 3D or 2D or some other rotation, for example, then it's fine, because if you see this spinning 3D cube, although the animations seems a bit complicated, you can see that the number there, they don't change. It keeps at the same number, which means that for every animation frame where I rotate this spinning cube, there's nothing much happening there between the CPU and GPU, except the CPU tells the GPU, hey, please now use a different transformation matrix for this texture. Same if you do opacity change. So in this case, I do a rotation and opacity change at the same time. That's fine, and that will be very high performing, because the CPU doesn't need to tell the GPU, please recapture this and send it again. So one operation, one initialization, and for every animation frame, it's just a matter of modifying the opacity and modifying the transformation. Now, if you've seen the predictable demo from 3JS, a very nice graphic library, let me show it. This is pretty cool. Even if you view this demo on a mobile device, on a tablet, for example, it is very smooth. Because what it does is to prepare all the elements and then send it once as GPU textures. And then when you manipulate this is a matter of telling the GPU, hey, please use new transformation matrix. Very lightweight, very minimal, high performance. And there's a bunch of other demos. For example, movie show example from Montage is a nice examples where you can have animation on a curve, and that will still perform nicely even on a mobile device, because it doesn't involve the recapturing and capturing of DOM elements. If you check this Photon CSS Lighting, and then you toggle between lighting enable and lighting disable, you're going to see that enabling lighting will cause a lot of texture upload, because you change the color. And this is also a very nice example where you can build a first-person shooter using CSS. And that performs nicely again, because as long as you don't change the lighting very much, then it will be just a matrix transformation, matrix manipulation. Where's that montage? Yeah. Here you can see that if I scroll this, the number there changes as it comes to the front, the view, but otherwise it will be pretty stable. So when I do this animation, the GPU needs to do very little amount of work, and that's why it's pretty smooth. Filter is another thing. As long as you play with filters, change some elements to have different colors, add some drop shadows and so on. This just tells the GPU to use different shader. It doesn't need to recapture that element. If you build some games, sometimes you need to respond to the user reaction. And for example, if you build a game where there's a paddle and there's a ball, you need to define where the ball moves depending on how the user behaves or responds to the ball. And if you kick the animation based on JavaScript, you're going to miss at least 2 timer ticks. One is for the animation end event, and then one is to kick the next animation. So one of the things that you can use is to prepare both animations, so you know either it's going to go left or right, and hide it immediately as soon as you know which one is according to the user reaction. As I've said before, in the movie show example, this is a very nice case where you don't need to create this movie poster every single time, because there's only so many you can see on the screen. So you just need to swap the contents, and therefore you don't need to force a new texture creation all the time. And because the user can only move either to the left or the right, then you can sort of preempt that and prepare some texture, hide it off screen, and then show it immediately at the right time. One of the important things of using the rendering using the GPU is to avoid texture upload, because you need to think the GPU like a cache. So if you go crazy and translate 3D every single element, that is not a wise move. Now, I've shown before that color transition will cause a texture upload, because in this case, if I change from blue to green, there's no way for the GPU to keep that blue content and then change it to green, unless you use filter, of course. So one of the tricks that you can do is to do a superimpose element. So where's that thing? So for example, this is a very simple demo, like I mentioned before. But you see the number stays at 1. And the trick is because actually I have 2 boxes there. And then they sit on top of each other, and their color, I never change them. So what I change is the opacity. So the effect is that this will create a box as if it changes the color, although it doesn't. The drawback, of course, you need twice the amount of memory, so unless you do it carefully, your GPU memory will explode. But this is fine for subtle animation and something that you do for 2 seconds as opposed to for the entire life cycle of a web page. So again, blending is something that you can use to minimize the amount of texture upload. So as anyone who lives in big cities, you know that a car doesn't tell you anything on how fast you can go from point A to point B, because if you hit a freeway that looks like a parking lot, then it doesn't help that much. So because we're in California, I changed it to Tesla. So if you want to maximize the power of the GPU, you have to be careful to minimize the texture upload and minimize the amount of texture. So wrapping up, you've seen in a 10,000-foot overview how loader works and how WebKit layouts stuff via render tree and how particular render objects are painted, and of course some use cases of hardware acceleration. So if you know what is expensive, what is not expensive but ugly, then you can do feature cost analysis. It's also important not to fight the rendering engine. WebKit improves a lot, so there will be threaded HTML parser with Google Chrome, and in Chromium there will be threaded compositor. And if you try to redo what the browser is doing, at some point it will cancel your optimization. If you use CSS animation, the browser knows how to do CSS animation very nicely, so it can schedule all the twinning, and it won't block your UI thread. It doesn't cause any JavaScript garbage collector because it happens on different process, etc. So don't assume that just by, say, throwing Translate 3D or whatever, then my page will perform very nicely. Always use all the tools or the metrics that is available to you and make the right decision. So hopefully by knowing all of this stuff, you will be able to build a great web apps. Thank you very much.